Hello. So in the previous lectures, we looked at um, buck converters, how to linearize them, tune PIDs for buck converters to essentially get constant voltage out of them throughout the load range, and all of that. And right now, what I want to discuss is the concept of maximum power point tracking. And this applies to solar panels because we're essentially going to use that buck converter as the first stage of a solar charger for the batteries of the car, right? So we definitely need to look at solar panels. So I'll assume that the theoretical knowledge is in order, again, about the operation of solar panels, what a module is, what a string is, and the works. And instead of discussing the operation of solar panels, I'm going to discuss why we need MPPTs, the shortcomings of MPPTs, how to implement them with a very high level discussion. And we'll look at newer techniques, specifically the technique I used for the maximum power point tracker that I used to charge the batteries and things of similar nature. In the next lecture, we'll then look at the MATLAB implementation of a real-life MPPT. Right, without further ado, let's get down to business. What you see here in this figure is the typical output from a solar cell, solar panel, solar module, whatever the case may be, right? What happens is the maximum power point varies. Let's assume that at any given time, that this is the voltage you're putting through to your solar panel or to your load. This is essentially the voltage across the solar panel. Here, this line that I'm highlighting over here. So if you're then putting this much across your load and you're drawing this much current, that means you're essentially getting this much power out of your solar panels. And that is shy of your maximum power, meaning you're not getting full utilization of that solar panel. That's not right. What if you then increase the voltage indefinitely and you increase it to this point? Still, you're not getting full maximization of that solar panel. And somewhere in between these two extreme points lies what we call the MPP, not the MMP. I don't know what I was thinking there, which is the maximum power point, the voltage at which you're going to get maximum power for that specific load. So let's assume that you've got whatever load that you have and you're pulling this much current. What we notice here is that the maximum power point does not necessarily occur at the peak current point, because right over here, the current is constant and it starts decreasing slightly over here. And this is where we get the maximum power point. So if you were to just blindly go about this and pull whatever current at whatever voltage you're getting out of your solar panel, you will most probably not be using your solar panels at 100% utilization. That's bad because you want to get as much power out of these things as possible. So how do we then ensure that we're operating very close to this region? Because the method I'm going to discuss here is more of a method that oscillates around the region, not necessarily stays there, but it's a lot better than going in there blindly. And what I want to discuss with you is a traditional method known as perturb and observe, where you make slight changes in the voltage and you look at the changes in power, and based on the changes in the power output, you make another change either to the right or to the left. Let's look at a flow diagram that's going to illustrate this a little bit better. And here's this flow diagram. Let me see if I can fit this in the screen in its entirety. Voila. Right. So what we want to do in this perturb and observe algorithm is we want to measure the voltage at state K and the current at state K. What this means is we want to measure the voltage right now and see what it is, measure the current and see what it is. Then we calculate the power based on these two parameters, right? If we then check, is the power that we've just measured greater or less than the power that was measured before? Meaning if this is the second time that we're measuring, we look at whether this power that we've just measured this second time is greater or less than the power that we measured the first time. So if this power that we've just measured right now is greater, then delta P is going to be positive. If it's less, delta P is going to be negative. And based on whether this delta P is negative or positive, we then make the next decision. Now, what decision do we have to make? We need to check whether we're going to increase the voltage or decrease the voltage. And if you remember that buck converter, we increase or decrease the voltage by changing the duty cycle, right? So let's assume that the power that we're getting over here is greater than 0, that is, it's positive. That means the power that we've just measured is greater than the previous power. So we're heading in the right direction. If that is the case, then we want to check when did this occur? Did it occur when we increased the duty cycle, or did it occur when we decreased the duty cycle? Put it another way, did it occur when we increased the voltage, or did it occur when we decreased the voltage? Right? Because we want to continue in the direction that increases the power. So if it occurred when we increase the voltage or when we increase the duty cycle, we keep increasing it. If it occurred when we decrease the duty cycle, we keep decreasing it. Now let's get an intuitive feeling of this by looking at this PV diagram or IPV diagram, if you will. Let's assume that we start off working at this point over here. And then we increase the voltage. And we see that once we increase the voltage, the power increases slightly. Now we're at this point. Then we decide, oh, okay, this is actually working. Let me increase the voltage again. Then you make that perturbation, and you see the power keeps increasing and increasing and increasing and increasing, right? Until you get to the peak. So that's the intuition behind the perturb and observe method. Let's look at the next extreme. What if we increase and it decreases, or we decrease and it increases? What if here delta P is negative, meaning our perturbation actually caused a decrease in power instead of an increase in power? Then we want to look at what we were doing. Did we increase the duty cycle, or did we decrease the duty cycle in order to cause this negative perturbation? Then we want to, if we were increasing the voltage, then we want to decrease it. We want to go in the opposite direction. If we're decreasing it, then we want to increase it to go to the opposite direction. Now let's look at the intuition behind that. Let's assume that we're at this point and we increase the voltage, but the power decreases. Because remember, when you go to the right, you're essentially increasing the voltage. So we go to the right, that means we'll be laying somewhere here on this power curve. So we increase the voltage, but this essentially decreases the power. So then what do we want to do? We see that increasing the voltage actually decreases the power. So we want to decrease the voltage so that the power increases, and we decrease it some more, decrease it some more, decrease it some more. But when we get to this point, the maximum power point, if we continue decreasing the voltage, guess what? The power starts decreasing. Then the other part of the algorithm kicks in and it says, okay, now I see that the power is decreasing with a decrease in voltage. So let me increase the voltage. Then it increases the voltage, gets to this point, and then it gets to that point again where, you know, if you increase the voltage, you start getting a decrease in power. So we see that with this method, we constantly oscillating around the maximum power point, very, very close to the maximum power point based on your step size, obviously, but we keep our operating point very, very close to the maximum power point, which is what we, you know, it's desirable. It's what we want to get. It's the utilization that we'd like to get out of our solar panels. So this is perfect. This is brilliant. We don't need any other methods, right? I mean, you've got other methods like incremental conductance and all of that. I'm not going to discuss those. So according to this, we don't need any other methods. Why would we even bother? Let's look at a scenario where you've got partially shaded panels. What do I mean by partial shading? By partial shading, I mean a situation of this nature. Say you've got trees, chimneys, other houses, cloudy conditions, whatever the case may be, that will cast shadows on your solar panels over here. And what this essentially does is these cells at the top here are at 1,000 watt per square meter irradiation, for instance. Whereas these ones here at the top, obviously it's 1,000, but at the bottom, let's say we're at 400 or 600 or whatever the case may be, because you can clearly see there's a difference in irradiance, right? So when this happens, the output voltage, which is dependent on the irradiance, will change, or the open circuit voltage, if you will. And instead of getting a power curve like this one, you're gonna get something like this purple curve over here, or something like this blue curve over here, right? And then we assume that you are operating at this voltage. And if we transpose that and we bring it down here, this corresponds to this power point on the purple curve. And guess what? That perturb and observe algorithm will get stuck here, because if it tries to decrease the voltage, rather to increase the voltage, it'll say that, hey, the power is decreasing, so let me go this way. And it tries to decrease it, and it says the power is decreasing, so let me go this way. And it's essentially stuck at a local minimum, rather at a local maximum point. Whereas where we want to function is at the global maximum point. This is the maximum power that you can get out of the solar panels. But that perturb and observe algorithm is still stuck over here. Same with the incremental conductance. You will experience similar features or a similar problem. Right. So how do we solve this? Is there a way of getting around this? I wish there was. If you are familiar with metaheuristics or metaheuristic algorithms, which is a branch in computer science, some would even call it artificial intelligence. I wouldn't go as far, but metaheuristics are a method that would allow us to get around these. What they essentially do is they allow you to accept bad decisions so that you can sort of search for that global maximum point and stay within it when you find that global maximum point. There are many metaheuristic algorithms out there, things like the genetic algorithm. You've got particle swarm optimization, bee colony, ant colony, gray wolf optimization. There's a whole, it's a whole study on its own. But what I'm going to discuss and what I used for the panel to charge the car is simulated annealing. It's actually one of the simplest local search algorithms that you can find out there, which has been implemented in various electrical applications and obviously applications outside the electrical field with great success. You can even use it to solve the traveling salesman problem, which is a very popular problem in the field of computer science and stochastic optimization problems. So how does this simulated annealing algorithm work? Sounds complicated. Let's first discuss what annealing is. Annealing is a concept from metallurgy, which involves heating up a metal and then letting it cool gradually. That is decreasing its temperature gradually. And by so doing, you're actually alleviating the internal stresses in that metal and you make it stronger. So that's what annealing is. So what we've tried to do with simulated annealing is simulate the annealing process of that metal or the cooling process of the metal. And we've taken a few concepts here and there, and we've joined them with other concepts that will make this optimization algorithm work a bit better. It is inherently probabilistic because it's a stochastic algorithm. And because it's a stochastic algorithm, it actually allows you to make bad decisions to try to get to a good decision. And I'll illustrate that with some code from Python. But before we go on over to Jupyter Notebook, I'm actually going to give you a brief overview of how these decisions are made and how we basically code a maximization or a minimization problem and using simulated annealing. Well, a rule of thumb or a point of interest is that all maximization problems can be coded as minimization problems, right? I'll show you that in a bit, but let's focus on the topic at hand right now. So what this simulated annealing does is it chooses a random state. In this case, in our case, a random state would be a random duty cycle between 0 and 1. Obviously, you can't choose a duty cycle that's greater than 1. So we choose a random state. And we assess what we call is the cost function, or the cost of this duty cycle. The cost in this case would be the power, right? And then we choose another random state, or we choose another state, and we assess its cost, and we compare the costs of the two. If it's a minimization problem, that is, we're attempting to minimize the cost, we want to check whether the cost of this, let's call this k plus 1, the one that we've recently chosen, and the one we chose before is k. We want to check whether k plus 1's cost is less than k's cost. If k plus 1's cost is less than k's cost, then we accept k plus 1 as our new solution. However, if it is worse than the previous state, then we choose a random number. And if this random number is greater than the result from this formula, then we accept that bad decision. Remember, we need a way to accept bad decisions, but we can't keep accepting bad decisions forever. And I'll show you how to do that. So we choose a random number, and if this random number that we've chosen is less than the cost, rather, if the random number that we've chosen is less than the result from this formula, then we accept the solution. If it's greater than the result from this formula, then we reject the solution. Why does this look chaotic and tricky? Does it involve luck? It doesn't involve luck. It's a probabilistic method that has been used for numerous applications, and it works. Let me show you an example on Python. So this is code that I did to solve multiple functions, actually, that you can get on Wikipedia. I think I've selected over here is the Himmelblau function from Wikipedia. And we know that the local minimum, or the global minimum, occurs at 0. Let me see if I can find a sketch for the Himmelblau function quickly. Looks something like this. So there it is. And these are your minima over there. 1, 2, 3, 4. And there are 4 of them that occur at different points. But what we do see is that the local minimum occurs at 0. At z equals 0, or z equals 0. Right. So really, Wikipedia? Anyway, it doesn't matter. So what we're trying to do is we're trying to see if we can find the global minimum, that being z equals to 0, z being the function, obviously, of this Himmelblau function. Right. So how do we go about doing that? So we'll obviously state the function there as z or z. And we choose 2 initial values for x and y. You can even pass these as random numbers if you want to. I felt lazy, I didn't want to do it, so I just passed them as 1 and 2. Right. And then we want to set the hyperparameters. The hyperparameters are factors that we need to set in order for this metaheuristic algorithm to work. The gray wolf optimization will have its own hyperparameters, PSO, that being particle swarm optimization, bee colony, ant colony, etc., etc. Hyperparameters are factors that you have to set in order for your metaheuristic algorithm to function, you know. So what we're going to set is the initial temperature, which is 1000. So we'll assume that we've heated up this metal to 1000 degrees Celsius. This is just for plotting so that I can plot the results of this entire operation a bit later on. More on that later. The important part is the number of iterations. right? How many times are we going to search? Or rather, let me put it this way. The number of neighborhoods that we're going to search, or the number of cities, if you will, that we're going to search. Then we decide within these 300 cities, how many houses are we going to go to? So if we pick, for instance, Joburg, and we say Joburg is one of our 300 cities, we want to take 15 houses in Joburg and search. Then we go to Pretoria, that will then be M equals 2 now. Then we search 15 houses in Pretoria. And then we go to Cape Town and so on and so on and so on and so forth, right? So that's the whole concept of these two. So this is the number of neighbors, or rather the number of neighborhoods, and this is the number of neighbors. Now, what is alpha? Alpha allows us to decrease our temperature because it's our cooling rate. Because obviously, as you iterate, after each iteration or after each city, you want to decrease your temperature because your metal is cooling down. And that allows you to accept less and less bad decision. And you'll see why it allows you to accept less and less bad decisions. Why do we want to accept less and less decisions as we increase our iterations? Because we want to converge. We want to converge towards that minimum point, or we want to converge towards that maximum. I've coded this as a minimization problem. So a negative no. So it's a minimization problem, right? And K is just a multiplicative factor for our random number because we want our random number to be between 0 and 1. That's all it does. So let me then show you how this operates, because this is the bricks and mortar, the bolts and nuts, if you will, of how this operates. We have two for loops. The first one iterates in M, and the second one iterates in N, right? So this one is nested in this one. Okay, so let's look at the N loop. That is the neighbors loop, not the neighborhood loops. We take two random numbers. We call them rand X and round 1. And then we check, right? Basically, what we want to do with these random numbers is we want to check whether we should increase or decrease our step, right? So we're going to start at a random point for X, which is 1, and we're starting at a random point for Y, which is 2. Then we want to check, should our next move be 2.1, for instance, or should it be 2.2? That's all we want to check. Or rather, should it be 2.1 or should it be 1.9? Because if it's 1.9, it means we've essentially decreased. And if it's 2.1, it means we've essentially increased, right? So that's all we want to check. So we check this, we take this random number, and then we see, is this random number greater than 0.5? If it is greater than 0.5, then we want to add our step size to that initial value. So basically this calculates the step size and it keeps it positive. And how we calculate that step size is we multiply a random number by this random number here, this random x2, which we worked out before. We multiply it by that k factor so that we keep it between 0 and 1. And then we take the step size and we add it in order to get the temporary or the next value of X, the next potential solution. If this random number is less than 0.5, guess what? Then we subtract, right? That's all this else does. If it's greater than 0.5, we add. If it's less than 0.5, we subtract. Okay, we do the same for Y as well, because this is essentially a multivariable function. And we add our step sizes to X temporary and Y temporary. Now, we then want to look at the objective, or rather the cost of this function based on these two values that we've worked out for X and Y. If the objective or the cost, the value of Z is less than the value of Z which we got with those random values, then we'll obviously accept. So what potential OBG does is it works out the value of Z based on these two factors over here, which we got from our random choosing algorithm, so to speak. Right. So now we have the potential objective, and this just works out the current objective based on X and Y, which we chose before. So now we've got these two objective values over here, potential objective and current objective. Before we come to the formula, let's look at what this piece of code does. Right. Then we want to check, is the potential objective, remember this is a minimization problem, is the potential objective less than the current objective? If the answer is yes, then you want to accept X temp and Y temp as potential solutions because they're getting you closer to where you want to be. They're getting you closer to that minimum, right? So you accept these two and you decide, yeah, I like these two, I'm going to take them. However, if a random number that we chose is less than the formula, we're still going to accept these two. So what on earth is this formula? What are you talking about when you're talking about a formula? Remember the formula that I spoke about here that's highlighted over here. So what we do is we select a random number and we use the potential objective that we got to get a value for this formula. If this random number is less than the formula, then we'll accept potential objective as we'll accept the values that gave us potential objective, meaning we'll accept X temp and Y temp. However, if the opposite is true, then we don't accept X temp and Y temp, and we still stick to our old values. So this essentially allows us to select bad decisions, right? And those bad decisions are what enable us to move away from the traps in the local minima or local maxima, if you will, and we can move towards the global minima or maxima, depending on what you're trying to work out. Right. So, and isn't this going to keep on accepting bad decision then? How do we make it stop, or how do we decrease the probability of accepting bad decision with every iteration? Well, remember when I initialized TO to 1,000, we actually have a cooling rate over here, which changes TO by a factor of 0.85 after every iteration of M, not every iteration of N. So we're going to check 15 neighbors using this temperature of 1,000. Then when we go to the next neighborhood, to the next value of M, then we check it using 850, then we decrease again, and so on and so on and so forth. And if you decrease this, the total value of formula will keep decreasing and decreasing and decreasing. And the likelihood or the probability that the random number is going to be less than formula will be much lower. It'll keep decreasing as well. And as we get closer and closer to the end of our iterations, then we are accepting less and less random or bad decisions. That's essentially how we make our stochastic algorithm converge towards a solution. Right. So I hope this makes sense. That's all this does. And let's run this piece of code and let's see what our solution is. So as we can see, we've got Z equals 0. And the value of X is 2.998, which is about 3. And the value of Y is 2.002, which is about 2. And what this graph does over here, it shows us the values that we got. And it also illustrates the importance of accepting bad decisions, because we started out here with our objective just slightly less than 60 rather. And it increased because we kept on accepting bad decisions. And accepting these bad decisions allowed us to get to a point where we started decreasing. And we got to this local minima over here. But then we saw that we're going to get stuck here. Let's accept bad decisions again. We accepted bad decisions and the objective increased instead of decreased. But those bad decisions allowed us then to decrease and decrease and decrease up until this point, which is a lot better than the 60 that we started at. And then we accepted bad decisions again, which caused us to increase, but accepting these bad decisions essentially allowed us to decrease. and so on and so on until we got to zero. So this is the fundamental operation or a very high level overview of how metaheuristic algorithms work. I know that this is a continuous problem, and what we're trying to solve is more of a combinatorial problem with this MPPT. But I'll show you how that is done on MATLAB, and we'll actually just implement it, run the code, use it within our buck converter that we linearized and we controlled, and introduce a couple of panels in there. I am not going to do the cell balancing and other battery circuits. I just bought those off the shelf. What I am going to do is the MPPT. So the next question that I usually get is, why not just buy an off-the-shelf MPPT? A, they're expensive, and B, why would I deny myself the pleasure of doing this, of running such beautiful code, of, the headaches of designing such an MPPT and just buy something that somebody else made when I can do it myself? Why would I do that? So no, I didn't want to buy an MPPT. So anyway, if you like this, please press the like button, subscribe. If you want to talk to me, I'm going to drop my Telegram handle in the comment section below or rather in the description. If you've got questions, comments, or you can hit me up on Telegram. And I'm going to holler at you later. Bye.